Yang, are you ready? You're all set? Okay. So our second talk today is from Yang Hu, who will tell us about, I think, using calculus to a calculus approach to the enumeration of topological vector bundles. All right, Yang, whenever you're ready.
Awesome, thank you so much. Can everybody hear me well, by the way? And can everybody see my screen? Cool. Thank you very much. I would like to thank everybody for joining. It's a great pleasure and honor to tell the story here. So the story today is about counting vector bundles, and more specifically, our objects of study here are topological complex vector bundles over complex projective spaces. So those are really classical objects, right? There's nothing equivariant, nothing fancy. However, perhaps a bit surprisingly, even topological vector bundles over projective spaces, those are far from being fully classified or even enumerated beyond a few small dimensional cases studied back in 1970s. We're going to review this piece of history a little bit later in the talk. But our goal today is to use a modern tool called Weiss Calculus to produce some enumeration results for topological complex vector bundles over complex projective spaces under some conditions which we will specify momentarily. Let's get started. Let's set up the stage by fixing some notations. So throughout this talk, we would say the C is a rank R bundle over X. That would always mean we have a topological complex vector bundle of complex rank R, unless otherwise stated. And we're going to write vect sub R of X to denote the set of isomorphism classes of rank R bundles over X. And this is a point where homotopy theory immediately comes into play, because over a reasonable space X, this set of rank R bundles over X is identified with the set of homotopy classes of maps from X to a classifying space, which we call BUR. And our favorite model for BUR is, of course, the complex corresponding of R-dimensional planes in C infinity. So we have this homotopy classification, and throughout this talk, we're not going to distinguish the isomorphism class of a bundle and the homotopy class of the map classifying the bundle. We're going to use these symbols interchangeably. Okay. Now, with this homotopy classification in hand, the goal of studying rank R bundles of X is so we end up analyzing homotopy classes maps from X to the classifying space. However, this is a difficult job in general. Just like measuring homotopy classes of maps between any two spaces is difficult. And there are two basic reasons that can explain this difficulty here. The algebraic reason is that this bracket xy is in general just a pointed set. There's no hope at all for that to have any group structure or any fancier structure. So we are in lack of algebraic structures. And on the geometric side, it's often challenging to come up with enough variants that can tell the difference between homotopy classes. Although there are standard ideas, for example, we can always look for invariance in cohomology theories, right? In the case when Y is the classifying BUR, and E is the cohomology theory we're looking for is good enough, we will have a theory of Cartesian classes, but those Cartesian classes invariants are far from being complete invariants. So let's recall the story right now. So for example, if E is a ring spectrum, now, a standard idea in algebraic topology to measure homotopy classes of maps between X and Y is just to put on the glasses of E cohomology, right? So we end up analyzing algebraic maps from E cohomology of Y to E cohomology of X. And sometimes this kind of consideration already tells us something about what can happen or what cannot happen, but not everything. Example, when Y is the classifying space BUR, and when E is complex oriented, then the E cohomology of Y is going to have a very nice form, as we have seen in Jack's talk, and we have a theory of Turing classes. For example, if we just take E to be the Eilenberg-MacLane spectrum HZ, that's the simplest complex-oriented ring spectrum. Former group law is just additive. Now the E cohomology of BUR is just the ordinary cohomology of class-infinite space with integer coefficients, and this is isomorphic to the polynomial ring over Z on R independent generators, where this ith generator Ci is of degree 2i. So we can treat them as universal classes, and if we have a rank R bundle over X, we can define its ith term class Ci to be the pullback of the universal class under the class-infinite map of the bundle. And this lives in degree 2i cohomology of the base space X with Z coefficients. We have a term class when I equals 1, so on until R. So those are invariants. Right, because isomorphic bundles have homotopic class-infinite maps, and homotopic maps induce the same map in cohomology. So those are cohomology invariants, good enough. But however, those are not complete invariants. So just because two vector bundles have the same data term classes, that does not mean that these two bundles are necessarily isomorphic. So let's perhaps do a quick example. Let's consider the set of rank 2 bundles over the 6 sphere. Now, by homotopy classification, this is, of course, homotopy classes mapped from S6 to BU2. And this actually factors through BSU2. And now by adjunction, this is just pi 5 of the unitary, special unitary group SU2, but we know that SU2 is homomorphic to the 3 sphere, so this is just homotopy group of sphere pi 5 S3, and a classical calculation shows that this is the group Z02. Right, so what this calculation tells us is that there are exactly two rank 2 bundles over the 6 sphere up to isomorphism. One corresponds to the trivial element of the group, and of course, that bundle is the trivial bundle of rank 2. But there's another one corresponding to the non-trivial element of the group. And this bundle is called an eta. So it's a rank 2 bundle, which is non-trivial. But this bundle must have trivial term classes. Right, because the first term class of this bundle lives in degree 2 cohomology of the 6 sphere, and the second cohomology lives in the degree 4 cohomology, and both groups are 0. We have a non-trivial bundle, but this bundle must have all term classes vanish. So we see that term classes fail to be complete invariants. There are lots of non-trivial bundles having trivial term data. And what motivates our study is to measure this failure precisely. So our motivation is to measure this failure precisely. Okay, and since we're here, let's talk about a few situations where term classes do serve as complete invariants for complex vector bundles. Let's talk about some situations when CIs determine complex vector bundles. The easiest case being the case of line bundles. So when the rank of the bundle equals 1, that's the case of line bundles. So vect 1 of X by homotopy classification is homotopy classes maps from X to BU1. Our favorite model for BU1 is, of course, CIP infinity, which also serves as the classifying the Eilenberg-MacLane space KC2. So this is identified with degree 2 cohomology effects with Z coefficients, and taking first term classes realizes this homomorphism. So tensor line bundles correspond exactly to adding degree 2 cohomology. So this is super clear. And another extreme is when the rank of the bundle is super large. And in that case, we end up analyzing stable bundles. So if we think about the map from BUR to BU, the standard inclusion, this map has a connectivity, right? This is two are connected. So what this means is that if the space X we map in has a dimension that is no greater than 2R, then mapping to BUR and mapping to BU makes no difference, right? So if this X has dimension no greater than 2R, then vect R of X is identified with homotopy classes mapped from X to BU, and that's the complex K theory. So that's reduced KU0 of X. And in good cases, for example, if X is the complex projective space CPN, because, for example, the Chern character is injective, we still see that the Chern classes are complete invariants. For stable bundles. So in that case, a bundle is trivial. So again, if anomotive, all its Chern classes vanish. Okay, and perhaps another case is, so another standard idea in homotopy theory to study homotopy class maps between two spaces is to do some localization. And let's take the rational localization, for example. So from the point of view of rational homotopy theory, rational local homotopy classes maps from X to BUR can be studied using maps between the rational models, right? Because the fundamental theorem rational homotopy theory is that rational homotopy types of simply connected spaces are modeled by isomorphism classes of nice algebraic objects. We have differential graded Lie algebras over Q as models. We have differential graded commutative algebras as models. We have Solomon algebras, minimal Solomon algebras. When we study this rational local homotopy class map, we can just study maps between their algebraic models, and taking rational model is, again, a contravariant functor. So we end up thinking about from rational model for BUR to the rational model for X. And again, this classifying B space BUR is nice enough in rational homotopy theory in the sense that they are formal, so that its rational model is quasi-isomorphic to its rational cohomology. So this rational model for BUR can be identified with polynomial ring over Q, again, adjoining R independent generators. This I's generator CI leaves a degree to I. So from this point of view, rational locally, a bundle is determined by its induced map on rational models, but because the domain is a polynomial algebra, any such homomorphism is determined by its value on the generators. And we can think of these as rational Chern classes of my bundle. And in that sense, we say that rational locally, Chern classes are still complete invariants for complex vector models. Okay. But however, this is not true integrally, as we have seen in the previous example. So in general, this vector R of X, which is homotopy classes maps from X to BUR, if we don't do any localization, and if we work unstably, this thing becomes much harder to compute and to detect. So this is harder to measure when working in the unstable range. By which we mean the rank R of the bundle is less than half the dimension of the base space, but greater than 1 because line bundles are determined by the first string class. Okay, so our goal here is to produce some enumeration results for bundles whose Turing classes all vanish in the case when X equals the complex projective space CPN or general N in the metastable range. So the metastable range is when the rank R of the bundle is still less than half dimension of the base space. So again, it's unstable, but it's not too unstable in the sense that this R is greater than or equal to 1/4 dimension. This is what we mean by the metastable range. Okay, is everything clear so far? Any questions? Cool. So let's fix some notations. We're working for the complex projective space CPN. So its homology over Z is a truncated polynomial ring, again, on one generator X in degree 2. We can identify that as the first Turing class of the topological bundle. So if we have any rank R bundle over CPN, then its ith Turing class is going to live in degree 2i cohomology of CPN, which is going to be some integer multiple of x power I. So to encode this data of Turing class, all I need is to remember this integer coefficient, right? So we're going to say that this rank R bundle is going to have first Turing class C1, second Turing class C2, and so on until R's Turing class CR, and all of them are just integers. Okay, so I'm going to write this vector C for the data of Turing classes for a rank R bundle over CPN. Okay, so we're gonna denote by vect sub R per C of CPN for the subset of rank R bundles over CPN with this fixed Turing class data. So it's the set of rank R bundles over CPN whose first Turing class equals C1, second Turing class equals C2, and so on. Okay, and the cardinality of this set, we're gonna denote by VRN with this Turing vector C. So this number remembers the number of rank R bundles over CPN with this fixed Turing class data. Is that clear? And finding this number is what we call Turing enumeration. And a special case of Turing enumeration is when the Turing data we fix is completely trivial. So we're going to write vect sub R upper 0 of CPN as the subset of rank R bundles over CPN with trivial Turing class data. And this cardinality we're going to write BRN0. So this is the number that records the number of rank R bundles over CPN whose Turing classes all vanish. And finding this number is what we call vanishing Turing enumeration. Okay, is the notation clear? Great. So here's our results. So for an unstable bundle over CPN, remember the unstable range is the rank R. The bundle is strictly less than the complex dimension of my projective space and greater than 1. So the first unstable case is when R equals n minus 1. So in other words, the co-rank is 1, the rank of the bundle is 1 less the complex dimension of the complex projective space. And the second unstable case is when this rank is 2 less the complex dimension of the projective space, when R equals n minus 2. So our first main theorem enumerates the number of rank n minus 1 bundles over CPN whose Turing classes all vanish. And that's the first unstable case. And the result is the following. It depends on the parity of n. So when n is odd, this enumeration result is a 2. So there are exactly 2 rank n minus 1 bundles over CPN whose Turing classes will vanish. Of course, one of them has to be the trivial bundle. So we have found a non-trivial rank n minus 1 bundle over CPN whose Turing classes will vanish. And when n is even, this enumeration is 1. So only trivial bundle can have trivial true data in that case. So that's what's happening in the first unstable case. Now, in the second unstable case, the situation is slightly more complicated. So for any n greater than equal to 3, we have the following enumeration results for rank n-2 bundles over CPN, whose Chern classes all vanish. And this time, this result is determined by the value of n modulo 24. And the result is summarized by this table. So let's do a quick example. For example, 2023 is 2016 plus 7. So this is 7 modulo 24. And this results is saying that there are exactly 4 rank 2021 bundles over CP 2023 whose Chern class will vanish. Of course, one of them is trivial, so we have 3 non-trivial rank 2021 bundles over CP 2023 with vanishing Chern classes. So we have measured the failure precisely. Okay, so are the results clear? Great. So at this point, let's recall a bit of history in the subject of studying unstable vector bundles over complex projective spaces. Again, the unstable range is when this rank R is strictly less than n, but greater than 1. So what is the smallest case here? The smallest case is rank 2 bundles over CP3, right? Because CP1 is just the 2 sphere, and for CP2, well, land bundles are C1 determined, and rank 2 bundles are already stable. So the smallest unstable case is the case of rank 2 bundles over CP3, and this is studied by Atiyah Rees. So in their 76 paper, they presented a full classification of such bundles. And in particular, they have the following enumeration result. So this is a general Chern enumeration. So given the Chern class data C1, C2, and at this point, let's remark that not every data of Chern classes can serve as actual Chern classes of unstable bundles. Those that can be realizable often have to satisfy some arithmetic conditions, and often these conditions are summarized by the Schwarzenberger condition. And the Schwarzenberger condition in this case is requiring that the product C1, C2 is even. So if both C1 and C2 are odd, there cannot be any rank 2 bundles over CP3 with that Chern data. But if C1 and C2 is even, there's the following enumeration. So this is a 2 if C1 is even, and this result is 1 if C1 is odd. So a corollary of this is the vanishing Chern enumeration, right? So if the Chern data here is just the trivial one, then this vanishing Chern enumeration is a 2, because in that case, C1 is even. And that corresponds to this special case of our result. Sorry, I should say this case. This is the first unstable case. And in the same paper, Atiyah Rees also gives a classification of rank 2 bundles over CP4. And in particular, there's the Chern enumeration result. So rank V24 with given C1, C2 that's allowable, that is always a 1. So in that case, there's no failure of Chern data being complete invariance. And furthermore, the cases of rank 2 bundles over CP5 and rank 2 bundles over CP6, those are studied by Switzer. And in particular, these Chern enumeration results are given. So for general CPN, we don't know much historically, except that Rees proved in 1709 that the vanishing term enumeration for rank 2 bundles over CPN for general N, which is greater than or equal to 5, this enumeration result is at least a 2. So what that means is vanishing term enumeration is in general non-trivial. So there is at least one non-trivial rank 2 bundle over CPN whose term class will vanish. But we don't know exactly how many. Okay. And let me also mention a recent result. That's the result of Morganopi, who gives a full classification of rank 3 bundles over CP5. And in particular, there's the term enumeration for V35 with given term data C1, C2, C3. And again, for these term data to be realizable, some Schwarzenberger condition has to be satisfied. But once we have that, this enumeration is a 3 if both C1 and C2 are 0 modular 3. And this result is 1 if C1 or C2 is non-zero log 3. And as a corollary, when this term data is completely trivial, so the vanishing term enumeration for rank 3 bundles over CP5, this result is a 3, because that case, both C1 and C2 are 0 modulo 3. And to compare that with our result, this corresponds to a special case of our enumeration. So here, when n is 5 modulo 24, our enumeration gives a 3. Great. So, are there any questions so far?
Yeah, I just want to make sure I understand the logic. So first of all, the vanishing term enumeration somehow like is like a kind of a different problem than term enumeration. It's not like some sort of
it's like a sub problem, right? So in general, you can fix any Chern class data. You can ask how many unstable bundles are there having that Chern class data. And a particular case is when this data is completely trivial, right? So you can measure.
Right, but you can't transfer the data from Chern class vanishing to other Chern.
We can do a little bit of transfer. For example, if you tensor with line bundles, that would move. So for example, if you have a rank 2 bundle over CP3 whose term classes all vanish, if you tensor that with the topological bundle, then that will move to the term data C1, C2 equals 2, 1. If you tensor that twice, you get 4, 2, and so on. Then you can do something like that. But in general, I would say the vanishing term enumeration is a different question. Great. Other questions? All right, so let's now explain our strategy for obtaining these enumerations. So in principle, to study the difference between stable and non-stable bundles, we would look for, again, the map from BUR to BU representing bundle stabilization and take its homotopy fiber, which is U mod UR. Right, for space X equals CPN, being stably trivial is the same as having trivial term data, right? So here, this vector R0 of CPN, in principle, this is to be identified with homotopy classes maps from CPN to U mod UR. So in principle, we need to make a computation here and record the cardinality of it, and that will give the enumeration. However, this is an unstable calculation, which is hard in general because the standard tools in stable homotopy theory, for example, Adams spectral sequence or Atiyah-Herzberg spectral sequence, are not available for those kind of unstable calculations. So our idea is to use a modern tool, which is Weiss calculus, to replace this unstable calculation by a stable one. Replace this unstable calculation by a stable calculation. And of course, there's a price to pay. We need to work through a range, and that is exactly the metastable range. So let's recall that for x equals CPN, a rank R bundle is metastable if the rank R is strictly smaller than n, but no less than half of n, right? So it's still stable, but not super stable. It's still unstable, but not super unstable. So the lemma here is that in the metastable range, vect R0 of CPN can be identified with homotopy classes maps now from CPN to Q suspension CP lower R infinity. So here, this Q, as usual, denotes loop infinity suspension. And this CP lower R infinity, as usual, denotes the standard projective space CP infinity, quotient by the skeleton CP R minus 1. And we're going to follow the usual notation to write this as curly brackets, which means stable maps from CPN to suspension CP lower R infinity. Okay, so this vanishing chain enumeration now becomes a stable calculation, and this kind of calculation, so this is a Billing group, and this is amenable to standard computational tools like Adams or Tia-Herzberg spectral sequences. Okay. And the black magic that does the job is the Weiss calculus. So let's talk about the philosophy of Weiss calculus a little bit. So Weiss calculus is a machinery that studies functors from a category of vector spaces to the category of pointed topological spaces. So here, this category J is essentially a category of vector spaces whose objects are finite dimensional vector spaces. They could be real vector spaces or complex vector spaces, depending on purpose. In the case of if we work over the real numbers, this theory is called orthogonal calculus. If we work over the field of complex numbers, this theory is called unitary calculus. In any case, those are finite dimensional real or complex vector spaces with inner product, all under a fixed universe, which is R infinity or C infinity, depending on our purpose. And the morphisms are linear maps which preserves the inner product. So in other words, those are linear isometric embeddings. So this category J is essentially a topological category, right? Because the morphism sets more VW are Stifel manifolds. If you work over R, you get real Stifel manifolds like O, W, modulo O of, you take a functional complement of V and W. And if you work over the complex numbers, you get complex Stifel manifolds. Okay, and standard examples for such functors from this category of vector spaces to pointed topological spaces include the functor sending a vector space V to VOV if we work in the over the reals, or functor sending V to VUV if V is a complex vector space. So those are inputs for this machinery, and the output is a tower of vibrations associated to each such functor F. And this tower is what we call the Weiss tower, or sometimes the Taylor tower of the functor F. And we're going to explain why this deserves to be called a Taylor tower in a second. So this is the tower of vibrations, and there's a comparison map from the original functor to this tower at each stage. And those comparison maps are compatible in the sense that each triangle like this has to be commutative. This in stage, this T and F is example of an n polynomial functor in the sense of Weiss. These homotopy fibers, those layers, so this LNF is the homotopy fiber of T and F mapping down to Tn minus 1 of F. So this is a fiber sequence, this is a fiber sequence, this is a fiber sequence, and so on. So this layer is an example of an n homogeneous functor in the sense of Weiss. And a fundamental theorem of Weiss calculus is that homogeneous functors are classified by spectra with actions of unitary groups. So n homogeneous functors are classified by UN spectra. And now this nth layer, as an example of n homogeneous functor, has to be of the following form, according to the theorem of Weiss. So it has to send a vector space V to the infinite loop space of the classifying spectrum. Let's denote that by theta n of F, smashed with S and V, and then HUN homotopy orbit. So here, this NV is n copies of V, so it's like Cn tensor V over C, and SNV is to take the sphere, UN here acts on this part of Cn, and the action here is the diagonal action. Okay, so what does this mean, right? So Weiss tower is a machinery that takes in some functor F, which often represents some unstable information. For example, if F of V is BUV, that's the information of unstable vector bundles. And what this machinery does is to resolve such unstable information into stable pieces. So those layers being infinite loop spaces are stable objects. And so is this bottom piece. So this Tn T0 of F is a stabilization by definition. So this is colimit F of V plus this T0F sends V to the homotopy colimit F of V plus CK as K goes to infinity. So this is F of C infinity. So when FV is BUV, this T0 of F for any V is BU. So this is the constant functor, and that represents stable bundles. So the bottom piece is some stable information, and so are all these layers. So the philosophy of this game is to approach the original functor F by piecing together the stable info in the Weiss tower of F. Okay, and now let me explain why this deserves to be called a Taylor tower and why this theory in general is called a calculus theory. And this is because there's an analogy to make with usual differential calculus. So in differential calculus, we study functions f from, say, R to R, continuous functions. If f is differentiable, we can take its derivative. If that's smooth, we can take all the derivatives, and we can gather all these derivatives together to form the Taylor series. So for example, the Taylor series, let's do it at the point 0. That's the sum of f derivative n of 0 divided by n factorial times x power n, where n goes from 0 to infinity. Now, if we look at this nth homogeneous piece, well, this analogy here was this nth homogeneous piece in the Weiss tower. So this derivative here is analogous to this classifying spectrum. So this classifying spectrum is what we call the Weiss derivative. Sorry. The nth Weiss derivative of the function f. And taking x power n is sort of like taking this SNV construction here. And finally, doing homotopy orbit is kind of a symmetrization, which is kind of dividing by n factorial. And people familiar with Goodwillie calculus would notice that in the Goodwillie setting, this is the homotopy orbit is h sigma n homotopy orbit, which feels more like a symmetrization. But here, taking HUN homotopy orbit is analogous to that. Okay, so that's the setup, and now we're going to focus on the functor f sending B to BUV. We're going to study the Weiss tower of BUV and gather the information of its layers. And this is studied by Grigorone in 2022. So for f equals the BUV functor, its nth derivative is identified with a mapping spectrum from a combinatorially constructed space, which we call Ln, to the suspension spectrum of the adjoint representation sphere of UN. And once we have that, the nth layer of f can be written down immediately. So Ln f on a vector space V is the infinite loop space on map from Ln to special infinity as ADN smash with SNV and then take HUN homotopy orbit. So this is good enough, but in general, this mapping spectrum doesn't have a homotopy type that we can easily describe, but except for the first layer. So if n is 1, now this L1f of V is going to be loop infinity, suspension infinity on, so here this L1 is the zero sphere and AD1, S81 is the S1 with trivial U1 action. So this thing is loop infinity, suspension infinity on sigma SP with HU1 homotopy orbit, right? So this is Q sigma SV HU1. And in the special case, when B equals the standard complex vector space CR, we notice that this is Q sigma, so this HCR HU1 is the tone space of the R copies of the topological line bundle for BU1. Right, and we can call this Q sigma CP lower R infinity because this tone space is the study projected space. Okay. So great. And for the higher layers, we also have part information, again, given by Grigorone. So in general, this nth derivative is, we know that it is rationally contractible. For all n greater than 1. And integrally, it is contractible unless n is a prime power. And furthermore, there's some cohomology information that we can determine. For example, the HFP cohomology of the P power kth derivative of the BUV functor. We know that it is free over the subalgebra AK-1 of the standard algebra. But what we're going to learn from the results of Grigorone is simply that in general, those derivatives are highly connected. And by highly connected, I just mean zero connected. So sigma n of f is just zero connected. This is because this Ln is a CW complex of dimension n squared minus 1, and this adjoint representation is of dimension n squared. Okay, so we're gonna take advantage of this. So this will tell us that if in the case n equals p to the k, so L p k f of b, just loop infinity, sigma p to the kf, smash spk times b, hu pk homotopy orbit. Now this thing is gonna, so the first non-trivial cohomology, this is going to appear in degree no less than 1 plus 2 times p to the k times the complex dimension of the vector space V. This just follows from the fact that this derivative is zero connected. And as a special case, if p equals 2 and k is 1, so we end up thinking about the second layer. Now this L2f of V is at least 4 times the complex dimension of V connected. And if V is the standard vector space CR, then this is 4R connected. Okay, so the upshot is that now to study unstable vector bundles over CPN, we can just map CPN to the Weiss tower of BUV. So this is what we got. And we know that the bottom layer is just BU, it's the constant functor. So after taking pi 0, this will be stable bundles. And this first layer is something we can explicitly written down. This is Q sigma CP lower R infinity. And those higher layers are more mysterious, but we know that they are highly connected. So the second layer, when V is the standard CR, is already 4R connected. And the higher layer is even more highly connected. So that means if the complex dimension of CPN we map in, which is 2n, if that thing is no greater than 4R, right? So in other words, if R is greater than or equal to half of n, then all these maps are going to be pi 0 isomorphisms because now CPN to L2f of CR is going to vanish. So this is a pi 0 isomorphism, this is a pi 0 isomorphism, and so on. So what we get at the end is an exact sequence. So this, after evaluating at V equals C to the R within this range, right? Now we are just going to focus on the bottom fiber sequence. So after taking pi 0, we get pi star alongside sequence. We get that, so here, this thing is just a pointed set, but we can still talk about exactness, which exactly means things here, so rank R bundles over CPN, which maps to the 0 element there, which exactly means bundles having trivial return data, is measured by the previous group, and the term before that is 0 because that's complex k -1 of CPN, and that vanishes. So as a consequence, this tells us that vector R0 of CPN is identified with maps from CPN to Q sigma CP lower R infinity, which is stable maps from CPN to suspension CP lower R infinity. And this works in the unstable range only. So the unstable range is when R is less than n, but greater than or equal to half of n. So our main results are going to be proved by calculating these stable mapping sets, so these are groups. Our first main theorem is the first unstable case, which enumerates rank n-1 bundles over CPN whose Chern class will vanish. We're going to make this calculation here when R is n-1. Here, only prime 2 is going to contribute, and this calculation is a z mod 2 if n is odd and 0 if n is even. So this gives the enumeration in the first unstable case. And in the second unstable case, we take R to be n-2 and make this calculation. Here, there are two primes that can contribute. So we have a prime 2 calculation and a prime 3 calculation. We combine them, we get this integral calculation. So prime 5 is not, or primes larger than 5 are not gonna contribute to this calculation. So the plan for these calculations is to first calculate the stable homotopies of this target suspension CP low R infinity through a range that satisfies our need. I'm going to do that using atom spectral sequence. And we're going to treat these kind of calculations as cohomology calculations whose coefficient ranges are exactly those stable homotopies. And we run through the Atiyah-Hertzberg spectral sequence to obtain these desired calculations. So I guess I'm out of time. So let's, maybe I should stop here.
All right, let's thank Yang.